Hey guys, welcome back to another episode of the Real Hacker Hours podcast. Today we're going to be continuing with trying to evaluate that one Semgrep tool I made by running it against various targets and seeing if it finds any bugs. Today this is another HTTP server off of GitHub, so we're going to look at it. These are the results from the sprintf %s rule, and we see it flagged 11 different instances, so we're going to take a look at that. Looking at these, you can see they're all in the httpd.c file, so I'm going to go ahead and open that. Okay, here's the file. Line 337, 338, 339, and 340. Let's go there. 337, which is right here. Okay, build the HTTP response body. Client error. Okay, this send the response. Message, content type, content length. Okay, so we see here that what this function is responsible for doing is sending an HTTP response, judging from the function name client error. I'm guessing it occurs when an error occurs and it needs to send some just diagnostic information back. I do not know how much control I'm going to have over the input, so I'm going to take a look at some of these other ones. You see line 421, so let's take a look at that. Serve static, send response to the client, server name, %s. Okay, connection close, content length, content type. Okay, cool. So what we're seeing here is it's using sprintf to effectively build the various responses that it will, or build the HTTP responses that it will send back to the client when it gets a request. And we see the file for a lot of them uses %s. So if we control the inputs to it, we should be able to get a bug, assuming there isn't proper size checks on the data. We see here serve static, file name, file size. We probably control file name. Get file type. File type is a char pointer. Let's take a look at this. Is it in this? No, it is not in here. Guessing HTTP utils. I might need to do a grep to find it. Nope. Yeah, I'm gonna need to do a rep. Oh, it's to find an HTTPD. Okay, here we go. Star copy. File type. Okay, so we're seeing here what it's doing is it's running a bunch of comparisons against the file name, and depending on what it is, it will copy a static string, so it doesn't look like we'll be able to get much functionality from that. Okay, let's take a look at some of these other sprintfs. So 421, I think we already looked at this, but content type. It's writing. Oh. Okay, so buff is the char pointer it's using, and what it's doing is it's continually just like writing it to itself. So you see it starts off with writing HTTP OK, then the server name, connection closed, that doesn't have any new stuff written, file size, and then the file type. I don't think we're going to be able, judging from what you've really seen, I don't think we're going to be able to control any of these, so I'm going to look elsewhere. 346, 345, and 344, let's take a look at those. Okay, cool. Build the HTTP response body. Okay, again, we're seeing the same thing where it just continuously writes, stores the HTTP response in body and just writes itself to it. And we also see this part of client error, which I believe we just looked at. We're going to look at it again. Error title, error number, short message. Not sure. Might be able to control the message. Long message, cause, body, httpd.name. Path, constant type. Okay, I'm primarily looking at this. This is where the different, where the remaining sprintf %s were flagged. So looking at here, depending on short message and long message, how those values are generated, we might be able to, we might have a bug here that we can use. I'm going to go ahead and look for this. Okay, so we're seeing here is client error. The first argument is a file descriptor. Second one is the file name, as we're seeing in these multiple instances, which I'm assuming that's something that we have control over, because when you make an HTTP request to a particular resource, and I'm assuming the resource is what the file name is, the next three arguments just appear to be static strings, so probably don't care too much about them. Looking at the definition for client errors, see the first one's a file descriptor. Second one, calls, which is a constant char pointer, or at least defined in here. That we do control. Looking here, okay, cool. We see here that calls is being written right here in this individual sprintf to a stack buffer. So we might have something not found. We see here that one of the errors is it does not find it. So what I'm guessing is we might be able to trigger this individual client error call by making HTTP request to a resource that does not actually exist. And that should call client error, with the calls being the resource name that we defined. Let's see if this is actually accurate or not. ls site sudo gdb gdbd. I'm just going to run this on port 5555. I think it's TACP5555, and then say probably I got that right. Cool. Set follow fork mode child, and let's break on client error. Continue. Now I'm just going to make a wget call to myself at port 5555. I believe that's what it was, and I'm going to request something that does not exist. Okay, that did not appear to work. Why? 5555. Let's see, is it listening? 5555. 127.0.0.0. So we see here it is indeed a listening on 0.0.0.0, which is basically all interfaces, and we're sending on port 5555. We're sending a request there. Why is it not? Hang on. Not listening anymore. Let's try it now. Sudo p80 sign. Okay, cool. So now we're seeing they're able to get it. Cat 5. Okay, says it works. Okay, cool. So we have it just running on port 5, not port 5, port 80, and it works. Let's try running in GDB. Tech P80 site. Set follow fork mode child. It appears to be a multi-threaded target, so we need to set the follow fork mode to follow the child process. Since that is probably what actually handles the processing of dealing with the client. So that, and next we'll set a breakpoint for client error. Continue, and let's try this. Interrupted from eval. So we see that this is no longer working, which makes me suspicious. It might be the how we're running in the debugger. I'm gonna try running this. Set follow fork move child break on client error run tech P80 site. Okay, let's try this. CD temp. Okay, we sent this response and we see that we are able to hit client error. So it's just something that we were doing with the debugger where we were running it and then pausing it and then setting the debug options that was messing with it, which I kind of got that all that we were messing with it from the interrupted from ePull await. So cool, we're here and we see that, what is it? The second argument is the calls RDI, RSI. Okay, we see that's there. So we are seeing that it is operating how we expect it to be interrupted from ePull rate. So I'm just going to go ahead and run it again. How big is the stack buffer? Let's see. It is equal to max buff, which this is a constant. I'm guessing that's defined as 8,192. Max IO buffer size. Where is this? So if we can send in a large enough string, there aren't any size checks. It should have another stack buff. I wonder. Okay, the first thing I'm gonna try doing is most definitely a better way to do this, but oh well. How big was this? 8,092. I'm just gonna go for 10,000. Cool, copy that. We're gonna get this working. Set follow fork mode child. Break on client error. Run port 80 site. And now, let's see, does this work? Okay, we see we got here with a ton of zeros, only 4,090. Okay, let's see what happens. I don't think this is going to overflow because what I'm guessing what happens is it will only scan in like 4,096 bytes or something like that. Yeah, okay, cool. So, what can we do? As we saw from, where was it? Okay, never mind. I had it up earlier, but I'm not going to bring it up again. As you saw earlier, the file size that we got was only 4096. I'm pretty sure max line makes sense. That's right here. Get name info. Yeah, read method URI version. It's because, yeah, this right here defines it as the max size to scan in as being that. Now, one thing that was a bit interesting that we saw is you see the directory name is prepended to it, and we saw with our request we did not specify that. So we might be able to do is if you create a large enough directory, you might be able to compensate for the extra like 4,000 or so bytes. So I'm going to go ahead and try that. Okay, cool. How can I do this? I will need to exit out of here. Print 0 times. I'm going to pause it while I just create some directories to set this up. Okay, so I set up the directory structure. Let's go ahead and give it a try. Okay. So we are here. Okay. Wait, did I set a breakpoint properly? Yeah. So I think it's obvious here that we got a stack overflow. Not. I think I made a mistake where I forgot to set the breakpoint. So I'm just gonna redo this. Break out client error. Set follow fork mode child. Okay, so the buffer overflow is happening sometime before the client error, which means there's a buff somewhere else that we aren't sure of. Could be, yeah, client error. So before client error executes, there's a buffer overflow somewhere that we're triggering. Yeah, call stack doesn't have anything for us since we just just overflowed it. 0. Switching to thread. Okay, so in order to find this out, there are a few different ways you can go about this. Probably like the easiest, at least initial way I'm thinking of is, let's see, how many bytes is this? Three length, 10,000. I'm going to place the zeros with ones. That should give us an indication as to if it's the directory, the resource we're requesting, or both that's overflowing it. And that knowledge should help guide us into finding exactly where it is. Okay, I copied it. Okay, we need to restart this. So follow fork mode child. Run there. Port 80, although I probably don't need to do that. Okay, so looking at here, we can see it. We can see that the stack has been smashed with ones, which tells me that it's probably ones that are doing this. So let's go ahead and just quickly look at worker thread, block all signals. I'm going to try it while one. It's probably this scanf right here that's doing it, I would assume. Buff max line. Yeah, okay, cool. So this loop right here, it's the primary loop which handles taking in new connections and assigning a new worker process or thread. Actually, it's a new thread to execute that. And we see here that it relies on the doit function to actually do that. I believe just through looking at this that scanf or scanf this is the function that's actually responsible where our buffer overflow is happening. So to verify that, let's go ahead and break there and see what happens. Okay, cool. We successfully broke there. Gonna step to the scanf. It's gonna take a second. Could just set a breakpoint and go there, but oh well. No, I'm lazy. I'm just gonna set a breakpoint for it. Where is the scanf happening? Scanf is happening here. I shall break there. Okay, see that RAP is something that looks like it's what it's supposed to be. Step in, finish. Okay, so it isn't the scanf that's doing it. Log. Serve static. Wonder if it's. I'm just gonna step through here and see where it's giving us issues. Read requester. Parse URI. Parse URI. So it's the overflow is happening in this function. Parse URI. Stir copy. File name. Work directory. String concatenate. So stack is getting smashed in here, and when it returns, that's when it crashes. Question is, where in here is that happening? We're seeing star copy here, copying a static string, that's not it. Copying file name to work directory. This could be an overflow. However, it's copying it to a pointer that's passed in. So if it is an overflow, it's not happening in this function, which means let's bring it up here. And parse URI. We hit finish, which means that this stack gets overflowed, so it's not that. String concatenate file name. Well, the only local variable here is this sbuff, and we see that's only really referenced here. Stat. What does stat do? Is that a standard function? Display file or system status? I'm just gonna step through it and see what's happening, because what I'm seeing here, at least at first glance, it isn't making too much sense. hitting the up arrow. So follow fork mode child. Okay, we're running with that. Oh, I forgot to set a breakpoint. Break at parse URI. And now we can run it. Okay, cool. So here, how big is this function? About 50 to 100 instructions, not too bad. I'm gonna just step through and see what's going on here. Yes, saved return address is normal so far. Oh, I'm in store copy. Shrink concatenate. Okay, it looks like string length. String length. Let's finish this. RIP is still normal. String copy. I'm gonna full screen this so it's easier to read. Saved RIP equals this. So that start copy is not it. Let's continue. String length. Get the feeling this function, this stat function, is where the overflow actually happens. Okay, that didn't make sense. Oh, I'm just smooth braining this. I'm going to pause the stream for a second. Okay, I just thought of a way I can find out exactly where the overwrite is happening. I'm just going to use a write breakpoint for the saved return address and just see where it's getting written. So, there's also the slight possibility that we're only overwriting the stack canary. But which that would make sense with what we just saw, but I'm gonna not go down that route right now since that's a bit tough. So we need to first set follow fork mode child, break at parse URI, and let's run the target. So we're running it, cool. Actually, since it's multi-threaded, we might not need this follow fork mode child. Interrupted from equal rate. I'm gonna need to restart this. Okay, we see that we are here. Let's see, can we stack check fail, jump 276, compares it against our speed plus OX98. Do we see anything like that up here? No, it looks like that's where the stack canary is being held, I believe. Maybe I'm wrong. Oh well, let's info frame, RIP is right here. Info B. Okay, so if it gets overwritten, we should know. And let's continue. Okay, did the breakpoint get hit? Hit breakpoint 1. Full frame. So at this point, okay, it looks like Jeff right now is not decompiling this properly. Reason why do info frame is lists this. However, when you look at the call stack, it's very evident that the local stack has been overflowed. So, in addition to that, breakpoint B. Hardware watch points 2. Yeah, okay, cool. So, executes after 99. What I'm going to do is going to go ahead and restart this. Set follow fork mode. So follow fork parse URI. Let's run this and let's hit it. Okay, cool. We are here. Backtrace parse URI. So we saw in the previous iteration of this that at the instruction parse URI 99, stack is obviously overflowed, and looking at the source code for parse URI, I'm not seeing any repeating loops, so we can probably assume that it has a linear control flow, which means overflow most likely happens prior to that instruction. So it probably happens here. Looking at the functions called, we can see stir length, STP copy, stir length, and we're just going to look below this to see if there's any jumps back up to there. Jump back up to 61. Okay, so it could be that might be this star copy that's doing it, and then it's jumping back up to here since there's jump. Parse URI 61. Sterling. Okay, cool. It's probably, yeah, getting back to the point, it's probably either this STP copy that's overflowing it or the stir copy, so I'm just going to set breakpoints for both and investigate them individually. I will be using BT to check for a stack overflow instead of just looking at the saved return address, since we saw previously that isn't entirely accurate in this condition. Where is this for? That's for that. Set a breakpoint for here. It could also be another function call which is causing it to crash that I'm just not seeing. Let's just do one pass width for that. Jump, stir length not doing it. Another jump, stir length copy, which I set a breakpoint for already. And I'll set a breakpoint for that. I honestly don't think it's xstat that's causing the overflow, but I'm going to set a breakpoint just to be certain. Forgot that. Let's continue. Stir copy. Stop in it. Okay, the star copy did not do it. STP copy. We see a giant string. This might be it. Okay, so it is 100% without a doubt this STP copy that is doing it. SDR copy. Now, what we're seeing here is we see a star cat. Oh, actually, two star cats and a star copy. No STP copy. I believe what's happening is STP copy is just like a lower level function that I just will wrap it with all or replace star cat with star copy. Let's take a look at STP copy. Copy a string returning pointer to its end. I'm gonna pause the stream for a second while I look at what's the difference between this and star copy. Okay, cool. The main difference between star copy and STP copy apparently is with STP copy, it tells it that there is no overlap between the two. I believe I might have read this article wrong, but fairly identical, and I don't think for our purposes it doesn't really matter. But getting back to which of these is the real culprit here, star copy. Likely this one call is inline since it is a static string. Same thing with that one and that one. I've seen that behavior before with other compilers. I'm just assuming it is. We see here that there's only two functions called star copy and star cat that actually have a what's the right term? A non-constant source. So that's probably why the star copy and the star cat that we see. We see here star copy, which we see. Let me pull up the disassembly again, or not disassembly, assembly. Here, disassembly parse URI. Here we go. You see STP copy and star copy. We see here star cat is what's copying the URI, and star copy is copying the work directory. So it appears, and since it's we saw that it's the request or the URI that's overflowing it, it's this star cat right here that is actually causing the BOF. Now, as to why this parse URI function, which it's writing to a char pointer or another array, is overflowing this one. What I believe is happening there is, let's take a look here, writing to file name. So what pretty sure what's happening here is it's overwriting this stack frame right here, and it's overflowing so much that it's also overflowing the stack frame for this one. So that's why it's, even though it's writing to another function stack frame, it's just overflowing with so much data, it's also overflowing the stack frame for this function as well. As we've seen with looking at the call stack after we smashed it, there was a ton of extra data there, so it wouldn't be too implausible to consider them. And yeah, okay, cool. So we have the bug here. We found it. Now, this isn't the bug that we were initially looking at with Semgrep, but let's see if our Semgrep tool found it. Semgrep, Requiem, flag, starcat desk static, HTTPD. It did not flag it. You see here it only flagged two things in error.c, which it didn't flag here. I believe reason for that being is, I think the only starcat rule I have is if it's writing to a static size buffer, not just in general. So might want to add a rule for that. I'll look into it, but cool, we found a bug. Okay, I'm gonna sign off. Thank you guys for watching. See you next time.